Alright, the power rule, or the integral of something to, say, the n power dx, that's equal to x to the n plus 1 power divided by n plus 1 plus c. So add 1 to the power, divide by the new power. Okay. Alright, we cannot integrate the 6 trig functions. We don't have all the skills to do that yet. However, if you remember, the derivative of sine of x is cosine of x, and the derivative of cosine of x is sine of x. Right? Or is it negative sine of x? Alright, so what that means is we can integrate those two. We know that the integral of sine of x dx is equal to, now we don't want to just say cosine of x, because remember the derivative of cosine is a negative sine, so we have to say that's equal to negative cosine of x, because when you take the derivative of cosine again, you get negative sine, so the negatives would cancel out and you would get what you started with. The integral of cosine of x is equal to sine of x plus c, because the derivative of sine is cosine. So we want our answer right here that we get when you take the derivative of this answer that you get, you want to get your integrand, or what you are integrating. Alright, so that's a good thing that you can check your answers like that most of the time. You can take your answer, take the derivative of that answer, and you should get your integrand. Alright, now since we do know derivatives of all 6 trig functions, for example, we know that the derivative, let's see, of tangent is equal to what? Secant squared. So what that means is the integral of secant squared x must be equal to tangent x plus c. Alright, we know that the derivative of say secant x, what is that equal to? That's equal to secant x tangent x. So what that means is the integral of secant x tangent x then has to be equal to secant x plus c, because the derivative of secant is secant tangent. I really don't have to have this y up here since I don't have a y equals, but that's not a big deal. So the derivative of, it's another trig function, say cotangent x. We know that the derivative of cotangent is negative cosecant squared. So that would mean that the integral of cosecant squared x is going to have to be what? Negative cotangent x plus c. Alright, there's one more trig function, one more basic trig function, and that is cosecant x. The derivative of cosecant x is equal to negative cosecant x cotangent x. So that means the integral of cosecant x cotangent x has to be equal to negative cosecant x plus c. A lot of times students get the secant and tangent integrals and derivatives mixed up. So remember that tangent, the derivative of tangent is secant squared. So that would mean the integral of secant squared is tangent. And then even if students get this right, sometimes they get confused here between cotangent and cosecant. Here's how I remember the difference, or one way that you can remember the difference. If you can remember that the derivative of tangent is secant squared, what is the reciprocal of tangent? Cotangent. Its derivative is also squared. It's a different function, but its derivative is also squared. So tangent and cotangents are reciprocals of each other, and their derivatives are both to the second power. The same thing holds for secant. Secant, the derivative of secant is equal to two terms. Well, it won't be its reciprocal, but its cofunction, cosecant, its derivative also has two terms. And by the way, tangent and cotangent are cofunctions. Right? Tangent and cotangent are cofunctions. Secant and cosecant are cofunctions. And then sine and cosine, but those are the two easy ones. So you will need to know these derivatives. And in order to know the derivatives, you do have to know the derivatives. So, or maybe you will have to know these integrals. All right, let's say that. And to get integrals, usually you have to know derivatives. So if you did not learn all of those in Calculus 1, or they're still a little fuzzy, you might want to make index cards or review them until you can remember them. They're that important. Now, I'll work through just a couple of really quick examples, just to kind of give you a little more review on that, on the antiderivative or on integration. Let's say that I wanted to integrate 1 over x to the 4th. Okay, at first you may not see that we have to use the power rule. We have to rewrite the integrand, what I'm integrating here, in order to apply the power rule. Okay, so if I rewrite the integrand by moving x to the 4th to the numerator, that's going to be x to the negative 4. Now remember, if you add 1 and then divide by the new power, when you add 1 to -4, you get -3. So it's going to be x to the -3 divided by -3 plus c, or -1/3, or -1/3 times x cubed plus c. Never leave exponents negative. Always make them positive. Alright. Let's look at another example real quick. Let's say I had the integral of the cube root of x squared dx. So first I would want to write this as a rational power. So this is the integral of x to the 2/3 power. The power underneath is the top, the index is the bottom. So again, this is the power rule. So I had to rewrite this problem. Now I have to apply the power rule. So I add 1 to the new power and divide by the new power. So that's going to be x to the add 1 to 2/3. That's 1 2/3. Of course, we're not going to write it as a mixed number. That would be what? 5/3. And don't forget, you have to divide by the new power. Alright, so that's going to be equal to 3/5 x to the 5/3 plus c. Alright. Let's look at this one. Let's say I had the integral of 3 cosecant x dx. Then that's the same thing as 3 times the integral of cosecant x dx, or 3 times that integral, the integral of cosecant is negative cosecant x cotangent x plus c. So that's equal to -3 cosecant x cotangent x plus c. Alright, now let's do one more. Let's say I had the integral of 3x minus 5 over the square root of x dx. So I have the integral of a fraction. Now, here's something that you can never do. You cannot integrate the numerator and denominator separately. Ever, ever. If you try and work this problem like that, you will fail miserably. It doesn't matter if it's algebraic, trigonometric, you cannot just integrate a numerator and denominator separately. So you have to use a little algebra to rewrite it. So this is going to be the integral of 3x over the square root of x plus the integral of, or minus actually, the integral of 5 over the square root of x. Both of those are dx. That is important. Alright, so we have just two different problems. We split this up. What we use there is called term-wise division. We split this up into two terms. Now, simplify each term. Remember, that's x to the what? 1/2 power. Alright, and we want to write that 1/2 power. We want to write that in the numerator. So, if it's a positive 1/2 in the bottom, when I move it to the top, it'll be a negative 1/2. So I have 3 times x to the first times x to the negative 1/2. So it's going to be just x to the positive 1/2. Minus the integral of 5x to the negative 1/2. Now I can apply the power rule. So that is 3, add 1 to the power and divide by the new power. So that's going to be x to the 3/2 divided by 3/2 minus 5 x to the, add 1 to the power, that'll be 1/2 divided by 1/2 plus c. So of course we're not going to leave these fractions in the denominators. You flip and multiply. So this will be 2/3 times 3 when you flip and multiply. So that's 2 x to the 3/2 minus, flip that and multiply, that'll give you 10 x to the 1/2 plus c. Now, this is not the most correct answer because this is written out expanded. If you can ever factor anything out, the best way to write your final answer is in factored form. You've probably seen that in Calculus 1 whenever you were finding critical numbers and things like that. We have to use equations to actually solve for stuff. So it looks like I can factor a 2 out, and then you can factor out the smallest power, which is going to be to the 1/2. So it's going to be x to the 1/2. So what would that leave me here? X to the first, because 1 plus 1/2 would be 3/2 minus 5, and of course I did not factor out of this plus c. It just stays on the end like that. So in my mind, the most correct answer would be 2 times the square root of x times x minus 5 plus c. Because if I was using this in an application problem, there's a very good chance I would need it to be in that form to get answers. Summation notation looks like this. You would have this right here is a capital sigma, and then you'd have some expression out here. Maybe it's a function. So you're summing up some function, maybe from, we'll say f of x sub I, where I equals 0 to some number. And so what this would mean is you'd want to take and you'd want to figure out what is f of x sub O, or what is your initial x value. Then depending on how many values you want to plug in or how many you want to sum up, then you would say, and I did mine to 5, then it would be plus f of x sub 1. That would be a number that we would plug in. We would get a number out. Then we would add f of x sub 2 plus f of x sub 3 plus f of x sub 4 plus f of x sub 5. Alright, that's the way summation notation works. I don't go over a lot of that in here. We use a lot of summation notation in Calculus 3 series notation, but in here the main reason that we go over summation notation is to explain what's actually going on when we take an antiderivative. And so if we do have x values, then we're actually summing up pieces under a graph. Now, let's pretend that I had this function here. F of x equals negative x squared plus 5. So I'm going to graph that up here, even though I know all of you can probably picture it in your mind. I'm going to show you what that graph looks like. Alright, so let's say that I had negative x squared plus 5. Again, that's a pretty easy graph to visualize. It's just a parabola or a U-shaped graph with a y intersection point of 5 opening downward. If I was just to focus on the positive values, and let's say that, well, I wanted to know what the area of all of this stuff right here is. And so that's the function negative x squared plus 5. Now, I can't really tell by just looking at that what the area of that figure is. If I was to try to use some kind of geometry formula, maybe I could come up with one to find an area. I could give you a pretty good estimate, but my estimate would probably still be off by a couple of units. Okay. The way that I would estimate that, let's pretend that that I just wanted to try to use, you know, any type of method I could think of to estimate that. What I would probably do, and this is just in real layman's terms, you know, maybe I need to know about how much cardboard I need to make this type of figure. Okay? And I said I wanted to just look at this part right here. Just for a super rough estimate, you know, if I know this is 5 up here, and I know this is 0 on the x, that's about 2 on the y. I'm sorry, that's 5 on the y, that's about 2 on the x. Know what I'm thinking? Well, what if I just drew this common figure here? I just went straight up and over and made one big rectangle. Now, no, that's not going to be really close to the actual area, but it would be, you know, kind of close, maybe a couple units off. You know, if this side is 5 units tall on my y-axis, and this side here is, that's going to be 2 units, not 1, 2, on my x-axis. 5 times 2, you know, this rectangle here that I formed would be 10 square units. So, I know that my area is at least that. Alright. Well, how could I get a little closer? So I'm going to snip this thing out again. So what if I was to take and I was to form two rectangles? And then I could find the area of, let's see, the height of this rectangle right here would be 4, and the width would be 1, so that would be 4 square units. And then the height of this rectangle here is 5, and the width is 1. 5 times 1, that's 5 square units. So by making two rectangles, I figured out that the area is probably, a little closer to 9. Do you think that it's closer to 9 or that it's closer to 10? Well, the one we did first, where I made one big rectangle like this, remember that one, that was 10 square units. So which one do you think is closer to the actual area? The one where I made two rectangles is probably a little closer. Why? Because there's less wasted area. So by making one rectangle, I could get an estimate. By making two rectangles, I can get a better estimate. Well, what if I took that small space there and instead of 1 or 2, what if I made 4 rectangles? That means I would need to divide my x values here. If I say from here to here is 2, then, and it may not exactly be, and make 4 rectangles. Ooh, that one went up a little too far. Then you see I still have wasted space here on the outside, but it's not as much. Okay? And so if I was to find somehow, some way, which I can, I mean, all you have to do to get the height of the triangle is plug in the x value, and that'll give you the height. And then if we make 4 rectangles, and we know that this entire thing is 2 units, 2 divided by 4, each one would be 1/2 of a unit wide. So we could figure out an even closer estimate by making more and more rectangles. Okay? Well, this is one of the first ways that that people looked at this problem. How do you find the area under a curve? Well, one way, if the curve is oriented like this, either we can start on the left side, use left endpoints, and make rectangles. And if we do that, we're probably going to get something a little bit bigger than we're supposed to. Or what we could do is we could come to the right side and make rectangles. Let me show you what those would look like. So if I came to the right side and make rectangles, then what I would do is I'd just go up to the line and come in, up to the line, go up to my graph and coming in. Now the problem with this, yeah, it's going to be smaller than the actual. And it depends on how the graph is oriented, if it's opening upward or opening downward, as to whether the left endpoints give you something bigger or the right endpoints give you something smaller. But they're always going to give you one or the other. Okay? If you find the area of the rectangles that are where you go above the curve a little bit, that's called an upper sum. The upper sum is going to be, it's going to be an estimate, but it's going to be an upper estimate. So it's actually going to be larger than what you should get. Okay? If you're summing up rectangles below the curve and you have a little missing below the curve, then that's called a lower sum. So that's as small as your actual area can be, but it's going to be too small. It's not going to be the same. Alright, so let's say that I wanted to use 5 rectangles. To approximate the area of the region between x equals 0 and x equals 2. And I'm going to redraw this down here. Because this is a super rough sketch, but you might want to draw it on your picture. Make it a little bigger than what that graphing calculator had. Now I control my scale on my x and y axis, so if I was to graph it in the calculator, it may not look exactly like what I'm about to put down here, but I do want to make it a little larger just so we can see things. So let's say that, let's say 1, 2, 3, 4, 5 right here on the y, and I'm going to make my x scale a little bit larger. I'm going to say this is 1 here and this is 2 here. Alright, and so my curve is actually going to look something like this with this scale. It goes down and it's still decreasing right here. The actual x-intercept is going to be the square root of 5, so square root of 5 is just a little bit more than 2, but I'm stopping at x equals 2, so that's where I'm going to stop. So I'll just put a dotted line going down. So if I want to know the area here, I can do that by finding the upper and lower sum. The way that I do that, let's say I want to use 5 rectangles, so I need to divide this space here into 5 pieces. Alright, so what would the width of each rectangle have to be if I want 5 rectangles? I have 2 units and I want to divide that into 5 pieces. So the width of each rectangle that I make is going to be 2/5. Alright, so let's start at 0, and if I start on the left side, that's using the left endpoint for this particular graph. I'm starting at 0, so the height of my first rectangle at x equals 0 is going to be 5. Now, how much do I go over? Well, we said the width of each one is, so we can call that delta x. That means the change in x. The width of each one is 2/5. So I'm going to attempt to divvy these up. 1, let's see, there, there, and there. So what is this first one here? X equals 2/5. So if the width here is 2/5, that's going to be for my first rectangle. Then the width here is 2/5, So 2/5 plus 2/5 is 4/5. The width here is 2/5. So 4/5 plus 2/5 is 6/5. 6/5 plus 2/5 is 8/5. Now guess what? I better end right here. Let's see if I do. 2/5 plus 8/5 is 10/5. So that is the same as 10/5. So you kind of have that little check mechanism there. If you know the first x and the last x, then that last one better come out the way that it should. Again, how do you get the width of each rectangle? You say the number of units divided by the number of rectangles that you want to make. Now, starting with the left endpoints, that's the way I'm going to draw this first one, with left endpoints. Then, if I make my first rectangle and it's 2/5 of a unit wide, it's going to look something like this. Alright? And I started on the left using left endpoints. Now, the next rectangle on the left starts right here, and it's 2/5 units wide. The next rectangle, again, 2/5 units wide. You might want to draw over first. Draw the width first, then the length. Same here. And the same here. Now for this particular problem, you can see all of my rectangles are above the graph. And as long as it's a smooth curve and it's either increasing or decreasing, the curve is, then you're either going to be above or below. Left endpoints will give you above or below. Right endpoints will give you just the opposite. Okay, and I'll show you that in a second. But let's take this. Is this going to be a lower sum or an upper sum? An upper sum, right? Because the actual area that we figure out is going to be larger than what it would need to be, or what its actual area is. So how would I find this area? Well, I have to add up the area of all 5 rectangles. Okay? So how do I do that?
How do we find the height of the rectangle?
We need to find the height of the rectangles, or the length. We know what the width is, but we need to find the height of each rectangle. The way that we do that is by using the function. This function corresponds to this curve. So I need to put in the correct x value. So what was the x value for the first rectangle? 0. So we're going to say f of 0. That's the height. What's the width? 2/5. So we're going to say f of 0 times 2/5. That gives us the area of the first rectangle. Plus, what is our next x value? 2/5. F of 2/5 times, what's the width? Again, it's 2/5. So that's for this rectangle. Then, how do I get the area of the next rectangle? I have to say f of 4/5 times 2/5 plus f of 6/5 times 2/5 plus f of, what's the height of this rectangle? F of 8/5 times 2/5. Now, I said 5 rectangles. If you do f of 2, you're creating another rectangle. So you can't do that. I said 5. This gives us 1, 2, 3, 4, 5. And notice how many problems I have here. 1, 2, 3, 4, 5. It's a very common mistake for students to include that last right endpoint when we should not. Okay? Now, another way to write this right here, a shorter way, shorthand, I guess, you could say, okay, this is just 2/5 times f of 0 plus f of 2/5 plus f of 4/5 plus f of 6/5 plus f of 8/5. So that's a little shorter way to write that. You know, it's the same width every time, so all you have to do really is find these values, add them all up, and then say that times 2/5. Alright. So let's do that. Usually I don't go for decimals, but in this case we'll do some decimals. Because when I plug in these fractions, we're going to get decimals. I mean, I could probably just keep it as all fractions, but let's throw caution to the wind. Alright, so we have, what do we plug these into? Our function. What was our function? F of x equals negative x squared plus 5. Alright. So, plug in a 0. When you plug in a 0, you just get 5. Plus, plug in a 2/5. So 2 divided by 5 squared. And then I have to take the what of it? The opposite. The minus is in front. So that's negative 0.16 plus 5. There's the height. 4.48. Or actually 4.84. Sorry, I said it wrong. 4.84. Plus, plug in 4/5. That's 4 divided by 5. Square it. Make it negative and add it to 5. So the height of the next rectangle is 4.36. Alright. Plug in 5/6 into the function. So that's 5 divided by, or I'm sorry, 6/5. That's 6 divided by 5. 1.2, 1.2 squared. Make it negative, add it to 5. 3.56. Alright, and here's the last height of the last rectangle. Plug in 8/5. 8 divided by 5. Square that. Make it negative. Add 5 to it. 2.44. Alright, so if I want to find the area of my 5 rectangles, now I need to add all that up and then say it times 2/5. And 2/5 is 0.4. Alright, so I get 8.08. So what that means is I may not know what the area under this curve is, but I know that its upper sum, if I make 5 rectangles, I can estimate it to be about 8.08. So we know the actual will be less than that. So that's using left endpoints. Let's look at the same problem, and we'll actually be able to use some of these values again, so it won't take us as long this time. But let's look at the same problem if I was to use right endpoints. Alright, so I know this is 5. I'm going to space this x out a little bit and let that be that. We know what all these values are already. Okay. That's 2/5, 4/5, 6/5, 8/5, and 10/5, or 2. And that's where we stop. A function actually keeps going past 2, but we just want the area, we want an estimate of the area below the curve. Now I did this one with left endpoints, meaning I started on the left side, the far left, getting my values, or getting my height. Now what if I start with using the right endpoint? That means that the height of my first rectangle is going to be here on the right side. Okay, so there's my first rectangle on the right side. In this rectangle, we use this height here on the right side. In this rectangle, we use the height on the right side. Alright, and so you can see all of these leave a little space up here. So for this particular function, using right endpoints is going to give me a lower sum. You may say, well, how do I know if it's an upper sum or a lower sum? When you draw the rectangles, if they are below the curve, starting on the right side, then it's a lower sum. If they're above the curve, when you draw your rectangles, it's an upper sum. All right. Even if you don't see it graphically or visually, if you set the math up, you should get something. You're going to get one number larger than the other. Well, the larger number is the upper sum, the smaller number is the lower sum. So how do I figure these out? Well, if I'm starting here on the right side, my first height is found by saying f of 2. Now, I say f of 2, that's the height of the rectangle times the width, just like before. But what you can do is just put that on the outside of your parentheses, and we'll just do all the heights, add all those up, and then say that times the width of each one. So that's going to be f of 2 plus f of 8/5 plus f of 6/5 plus f of 4/5 plus f of 2/5. Now I know to stop there, because if I'm finding heights of rectangles, I have found 5, and that's how many I wanted to find. I wanted to use 5 rectangles. If I put that 6th one here, my answer is going to be wrong. So make sure that you only have ever how many rectangles the problem says to use. Make sure you have that many values plugged into F. Okay. So I told you earlier we'll be able to use some of these up here. See, we've already worked these out, so I can write those in. I'm going to have to figure out f of 2. That's pretty easy though. 2 squared is 4, so that's -4 plus 5, or 1. Now I can use these other values I've already found. F of 8/5, that's 2.44, plus f of 6/5, 3.56, plus f of 4/5, 4.36, plus f of 2/5, 4.84. So that's the heights of all 5 rectangles. Now I need to add those together and then say that times 2/5, and that'll give me my area. Alright, so you do all of that and you get 6.48. So we know that our actual area is somewhere between 8.08 units squared and 6.48 units squared. The more rectangles that I put under the curve or above the curve, the closer that I'm actually going to get to my exact area. Okay? That's the main reason why we go, or why we do upper sums and lower sums here. This was the problem that people were faced with before that we had the knowledge that we have today, or before we have the knowledge that was developed by some of the great mathematicians. So from what we have, we know that the actual area is somewhere between, we know that it's going to be greater than 6.48, and we know that it's going to be less than 8.08. As you increase the number of rectangles, the closer you get to the actual area. For example, for this same problem, if I let the number of rectangles equal 25, could you imagine doing that out by hand? No, that would take a long time. But before we had the mathematical knowledge of how to actually figure it out, you know, we had to do things like this. And if you do that, you get the lower sum to be 7.1712, and you get the upper sum to be 7.4912. So you see, it's not even super close by using n equals 25. Well, what if n equals 50? What if n equals 100? What if it equals 1,000? What if it equals 1,000,000? The larger n gets, the closer that we actually get to the area. Okay, so as our change in x here, as our change in x, or our delta x, gets smaller and smaller and smaller, then the closer that we get to the actual area. Okay, and so this would be our change in x. This would be our change in y. You know, our y's are changing as our x's are changing, but we really were saying that was like f of some x. And as we sum those up, the width times the height, as we sum those up, as we sum up an infinite number of those, say from 1 to infinity, then we're going to get the actual area under the curve, or under whatever region. And so what we're actually doing, it can be related to an integral. Now, if we take an infinite sum of regions, you can kind of relate that back to limits. You're letting, say, n approach infinity of some limit of a function. Alright, and what we're actually doing is we're taking a type of integral. And let me show you. This is a very important concept. We don't have a whole lot of time for me to work out a lot of these upper sums and lower sums, but I can work out more if you need me to.
Can we work out upper sum and lower sum using the trig function?
Let me show you real quick the point of this exercise, in my opinion. If we have this shape here with this function here, and we want to know the area under the curve, there's some way that I could relate this over to calculus. And the way I'm relating it over to calculus is an infinite number of rectangles. And if I sum up that infinite number of rectangles, what I'm actually doing is you can evaluate what we call a definite integral. Alright. And so, what do we want the change in x to be? We want that change in x to be very, very small, because we want to have an infinite number of rectangles. So we're letting that change in x actually approach 0, which is changing the number of our rectangles to infinity. Okay? And if we wanted to know the actual area, we could do that by calculating a definite integral. And the way we would set this up, and we have to have your function. It was negative x squared plus 5. And we knew that we wanted to look x between and equal to 0 and 2. So the way that you set that definite integral up to find the volume under the curve, you said it's equal to the integral from 0 to 2. The smaller number goes here on the bottom always. The larger number goes on the top of the function negative x squared plus 5 dx. So the way that we work this out, we first integrate. So that's going to be negative x cubed over 3 plus 5x. And then the notation that's used, usually you'll see either a line here or a bracket. I usually draw the end bracket, and I put my boundaries, my lower boundary 0, my upper boundary 2. Now the way this is evaluated, you need to work two problems now. You need to take and plug in the 2 in here. So if I plug the 2 in right here, that's going to be negative 8/3 plus 10. That's plugging in the 2 there and plugging in the 2 there. And then you have to say minus always. You say minus. Now plug in the lower boundary. Plug in a 0 there and plug in a 0 there. Now do not assume that you always get 0, because you don't. Depending on the function, plugging in a 0 could give you something different. On this one it doesn't though. Alright, so what is this? This is negative 8/3 and 10. Or negative 8/3 and 30/3. That's what 10 is. So that would be 22/3. If I punch in my calculator to get a decimal just to see, 22 divided by 3, 7.3 repeating, or 7 1/3. So it's about 7.33. Well, what were we getting earlier? Let's go back and look. Our actual area, 7.33. It fits both of them, 7.33. That's the actual 7 1/3. So you can find the area under a curve by taking the definite integral from the lower boundary to the upper boundary. The way you do that is you integrate first, then evaluate the top number, or the upper limit, minus the bottom number, or the bottom limit. Alright. So let's use that knowledge. Let's see if we can first find an upper sum and a lower sum to estimate the area under the curve of, let's say, f of x equals sine of x from x equals 0 to x equals pi over 2. All right. Yes, I will. We'll just say n equals 4. Let's see, making 4 rectangles. or using 4 rectangles. We want to do an upper and a lower sum. I'm going to graph that real quick. I mean, I could draw it out, but this program does a little bit better job than me. Let's see. Okay. And so the part that we're looking at here depending on your trig knowledge, which I hope is okay, this is 0 radians. Where would pi over 2 radians be? If you remember, the sine of pi over 2 is what? 1. So right here, that's going to be pi over 2 radians. Now, of course, I can't draw all that in this little small space, so I'm going to have to draw that here, just a rough sketch. All right. So here's our sine curve here. Goes through the origin, so it kind of looks like that. We're just talking about this region, say from x equals 0 to x equals pi over 2. Now, making 4 rectangles, what is the width of the entire figure from 0 to pi over 2? How many units is that between 0 and pi over 2? Pi over 2. So if we want to divide that into 4 even rectangles, 4 I guess rectangles that have the same width, you just divide that by 4. So dividing by 4 is the same as multiplying by 1/4. So each rectangle will have a width of pi over 8. Alright, so remember, I want 4 of those. So you can kind of check yourself if you draw these on here. I want 4. And so if this is x equals 0, then that's x equals pi over 4. I mean pi over 8, sorry. Now, add pi over 8 again, that's going to be 2 pi over 8. What's 2 pi over 8? Pi over 4. Add pi over 8 to that. Well, it was 2 pi over 8, so this will be what? 3 pi over 8. Now add pi over 8 to that, you get 4 pi over 8, which is pi over 2. So you can check and make sure that you got those x values right. Now, depending on whether we use the right or the left, if we use, on this particular problem, if we use the right endpoints, then all of our, let's see how our rectangles go. I believe, I may be off a little bit in the way I drew this, I believe they're going to be a little bit above. See, all of these are above. So this is going to give us an upper sum. So on this one, using right endpoints, how do I know they're right endpoints? Because I started on the right side and used that one first. That's going to give us an upper sum of, now each one of these was pi over 8 units wide. So I would multiply each height by pi over 8. Or, to shorten it up just a little, I'll just say f of all of my, get all of my heights, and then say it times that one width. So I started on the right, so f of pi over 2 plus f of 3 pi over 8 plus f of pi over 4 plus f of pi over 8. Now, stop there. We don't need 5 rectangles. We only have 4 rectangles, so we should only be plugging in 4 x values. Starting on the right side. Alright. Now, depending on your calculator, you might want to make sure it's in radians. You can probably get some better exact values if you're using some type of fancy calculator. Let's see. It's going to be pi over 8 times. What's my f? What do I plug this into? You have to plug it into the function that we were using, sine. So that's going to be, let's see, f of pi over 2 is going to be the sine of pi over 2, which is 1. So that's 1 plus. Now this one, yes, you're going to get some type of decimal. F of 3 pi over 8. So I'm going to say 3 times pi, use your pi button, equals, divided by 8 equals, so that's the radians, it's 1.178, and keep that in there if you're doing an estimate like this. And now I want to take the sine of that. Now I'm going to write down about 5 decimal places. 0.92388. I'll round to the 5th place. 0.92388. I hate rounding. Sometimes you have to do it. Alright. And now plus pi over 4. Well, that's 0.92388. Well, what is sine of pi over 4? You should know that. Square root of 2 over 2. I mean, you need that as a decimal, I guess, but you should know it's the square root of 2 over 2. That's common knowledge. Alright, 0.707, let's go to 5 places, 0.70711. Plus, now the sine of pi over 8. So pi divided by 8, take the sine of that, 0.38268. Double check that, 0.38268. Alright, so those are all my heights. So I can add those heights together. Alright, and then I want to say that times pi over 8. So times pi divided by 8. Alright, so my upper sum is 1.1837. So it's about 347. That's my upper boundary. My upper sum. Now I want to do the same thing, but I want to start over here on the left. So what is my first x value that I plug in on the left side? 0. That's right. So this is going to be using left endpoints. This will give me a lower sum. If One gives you an upper sum, the other would give you a lower sum. Alright, so the width is the same, it's pi over 8. And it's going to be times f of 0 plus f of pi over 8 plus f of pi over 4 plus f of 3 pi over 8. And I better stop there because that will give me 4 rectangles. The height of 4 different rectangles. Alright, I can use this work up here if you remember what they go to, what they correspond to. This last one is pi over 8, this one's pi over 4, this one is 3 pi over 8. Alright, I just don't use the pi over 2. I do have to figure out what f of 0 is, so what's the sine of 0? Everybody knows the sine of 0 is just 0. Common knowledge again, something we're pretty much born with. Alright, so add all those heights together. And say that times pi over 8. I'm going to round this to 5 places. That's 0.79076. Or 0.79077 if I round. So we know that our actual area has to be greater than 0.79077 and less than 1.18347. So now let's use a definite integral to figure out the actual area. So what was my x boundaries? Or what were my x boundaries? X equals 0 to x equals pi over 2. The function is sine of x. So if I take the integral, x equals 0 to x equals pi over 2 of sine of x dx, this is going to give me the actual area. The integral of sine is negative cosine. And now we're evaluating that from 0 to pi over 2. Remember what we have to do. We have to say, okay, that's negative cosine of pi over 2, then minus, don't forget, minus. And now I plug in a 0. But that's minus what? Negative cosine of 0. So don't get confused here. So this is negative. What's the cosine of pi over 2? 0. Minus negative. What's the cosine of 0? Cosine of 0 is 1. So it's equal to 1. So 1 square unit. Is 1 between what we should have got? Yes, it is. It is greater than 0.79077 It is less than 1.18347. So that is the actual area under the curve. So I won't work it all the way, but what if we wanted to find the area under the curve of f of x equals, let's make it something easy, like x squared from x equals 1 to x equals 4 using 8 rectangles. So I just want to show you, if we don't start at 0 here, how it affects the rectangles. So here's a real rough sketch of y equals x squared. You know, as x gets larger, that gets larger pretty quick. And it is parabolic. But if I'm going from, not from 0, but say like here at 1 to say 4, then what I'm getting would be the area of this space in here, under the curve and above the x-axis. So in here. So the distance from here to here is 3 units. So if we wanted 8 rectangles, then each rectangle is going to be 3 divided by 8. So that is our increment, or our change in our x, is 3/8. Now the left end point here is 1. So if I wanted 8 of these, then to get my next x value, I don't add 3/8 to 0, I have to add it to 1. So that's 8/8 plus 3/8 is 11/8. So you're starting on the left side, your first x would be 1, but then your next x, your x of 1, will be 11/8. Then to get the next one, you add 3/8 again. So that would be 14/8. Add 3/8 again, 17/8. You keep doing that, and you should end up at 4. If you don't end up at 4, then you have not added correctly. All right, let's see. So that was 20/8, 23/8, 26/8, 29/8. Now, this last one here is 32/8, or 4. Now keep in mind though, if you want to use the upper sum and the lower sum to estimate this, that you want to say this width times f of, well, we want to start at 1, so it'll be f of 1 plus f of 11/8 plus f of 14/8 plus f of 17/8, so on and so forth, until you get to the one before your your right endpoint. Add up all of those and say it times 3/8, you'll have an estimated area. Then start on the right side at 4. Do f of 4 plus f of 29/8 all the way until you get to this last one here, but don't use f of 1 because that will give you an extra rectangle. Then you'll have an upper and a lower sum, and we'll all be happy. Now, this is a lot harder than just doing this right here. Watch this. Here's how you find the actual area. The integral of x squared from 1 to 4 dx. Integrate x squared, you get x cubed over 3. evaluate that from 1 to 4. So what is that? That's 4 cubed over 3 minus 1 cubed over 3. 4 cubed is 4 times 4 is 16 times 4 is 64. So that's 64 over 3 minus 1 over 3, or 63 over 3, which is 21. So the actual area under the curve is 21 square units. So finding upper and lower sums is very tedious. But back before we had the knowledge of calculus and the way to sum up an infinite number of rectangles, that's the way that it had to be done.